Hello, my name is Jonas Braasch and I would like to welcome you to this presentation. Unfortunately, I can't be here for family reasons, but my co-author Jens Blauert is in the audience and he will be able to answer questions if wished. The idea for this talk comes out of a book project that Jens and I are co-editing with the title Technology of Binaural Understanding. Some of you might have heard about this book or even contributed to it. So in this book, we're trying to go from binaural hearing, where the goal is to understand, for example, how the auditory system can lateralize the sound, to a system where it can extract information that is important for pursuing tasks. For every biological system, the four main objectives are really the four F's: feeding, fighting, fleeing, and flirting or reproduction. From a functional binaural model perspective, we usually tend to look at a very narrow snapshot of time. I mean, if you think about it, binaural modeling has been around for, let's say, 3 generations if we count every generation to be 25 years. Of course, I'm talking here about biological generations and not academic generations. So the first generation of binaural models, of course, that was Lloyd Jeffries in 1948. Then Jens would be the second generation and I'll probably be the third generation. But first, those models were able to localize sounds in an anechoic environment, but that's not the case for most natural or physical environments. So we looked into models, for example, that can simulate the precedence effect, the so-called law of the first wavefront, that can eliminate the information for the reflections in similar ways that the auditory system does that. And that, of course, is very important for rooms like these that have plain walls and cause specular reflections. However, those rooms haven't been around for that long either. If you look at the modern concert hall, for example, and maybe the first one who would count for that is Vienna Musikvereinssaal, that's 1870, so that's about 6 generations that we have modern concert halls. If you go back to plain walls and rooms, we probably have to look around 5,000 years back or maybe longer. The earliest enclosures were natural caves. So the earliest evidence we have for musical instrument being played in the cave is the Hohlefels cave in Germany, where a 40,000-year-old flute was found within the cave. But that's a very different pattern because you don't have plain walls, but you have diffracted and curved walls that then cause more diffuse reflections. So the thing we really try to look in today is how does a model differentiate between specular reflections and diffuse reflections. So we used the binarily integrated cross-correlation autocorrelation mechanism, short BICAM, to analyze the acoustic environments that we discussed. The advantage of this algorithm is that the model can estimate binaural room impulse responses from a running signal and then make a determination first about the position of the direct signal, but also make assumptions about the positions of the early reflections. And that will be important so we can demonstrate how we envision the auditory system to deal with early reflections and diffuse reflections differently. So usually the way we do room impulse responses, of course, is we have a loudspeaker and then we have a binaural mannequin, and we run an MLS signal or an impulse signal or a Gaussian noise signal, and then we can measure the impulse response through deconvolution. We also have systems like Systune, where you have a person speaking into a closely positioned mic, but also being recorded by a binaural mannequin, and then you can look at the information between the closed microphone and the binaural mannequin to estimate a room impulse response. That, of course, is not what the auditory system does. So we're going to explain a method where you can get a fairly good estimate for signals recorded just with the binaural mannequin. So to say, you have a sender, the speaker, and you have a receiver that's connected to the auditory system. So in the bottom left, you see the architecture of the system. So as a traditional model, we have a bandpass filter bank that separates the signal into frequency bands, typically a third of an octave wide. In this case, it's used a gamma tone filter bank. So now in a traditional model, and we're not going to simulate auditory periphery like hair cells or so, you would have a cross-correlation unit that compares the left ear signal to the right ear signal. We have that too. That's the module CCLR, or you could measure it the other way around. That would be the module CCRL. But in addition, we also have two stages that compute the autocorrelation function for the left signal and the autocorrelation function for the right signal. The autocorrelation function for a signal that's sufficiently non-harmonic is a pretty good estimator about the positions of the reflections and the amplitudes. And then what we have is we have a second layer cross-correlation function on top of that, and that compares then the signals so we can estimate the temporal relationship between the left signal and the right signal, which is lost if we just compute the autocorrelation function, because the main peak will always be in the middle. That is where you compare the signal to itself. And then on top of that, I'm going to explain this all in stages. We're going to compute the binaural activity pattern, and we do that by using a running cross correlation on top of the two time-aligned autocorrelation functions. So let's look at the temporal performance of this model. So step one is we're going to measure the autocorrelation function for the left signal, the autocorrelation function for the right signal. And as you can see here in this example, we have a direct signal and we have two reflections. The problem is, in both cases, the autocorrelation functions have the main peak in the center, so there's no ITD preserved. So we need to get the ITD for the direct sound back, and if we realign the two autocorrelation functions by this ITD, we actually get a pretty good estimate for the ITD of the direct signal as well as the ITDs, ventral time differences, for the reflected signal. So in step two, what we do now is we basically compare the autocorrelation function to the cross-correlation function. So the autocorrelation function, in this case, left ear, and the cross-correlation function is the left and the right ear comparison. The trick is now that we say we're just going to analyze the side peaks. So we take a window that's indicated by the gray window with the dashed boundaries, and we say, well, since these are the same reflections, they should align in time. And so what we do is we use the cross-correlation function, and then based on this internal delay or shift that we get, KD, we realign the second cross-correlation function. That's step 3. And then what we're going to do is we're going to replace that cross-correlation function with the autocorrelation function. So we end with two autocorrelation functions that are time-aligned to each other. Now we preserve the ITD of the direct signal, but also the ITDs of the two reflections. Does the signal work perfectly? No, but it works within the boundaries to the performance of the auditory system. So if you have too many reflections and the amplitudes are too high, the model fails, but so does the auditory system, and we can outperform the auditory system by a small margin. In the next figure, we see the output of the BICAM model for a 22-second speech signal, spatialized with head-related transfer functions, as well as for reflections, also spatialized with head-related transfer functions. The main signal is located in the front with a 0 millisecond ITD. So you see the three axes, left, right. Then you have towards the front, back, the delay of the signal, and the height is then the intensity of the energy in that ITD, temporal delay, or reflection delay pattern. So you see the direct sound, but you also see activity for the 4 reflections, 2 to the left side and 2 to the right side. In the next example, we want to look into the output of the BICAM model for a signal with specular reflections versus a signal with just diffuse reflections. So on the left side, you see the output for a signal with 4 reflections. It's a speech signal, and the reflections are located at the positions where they're supposed to be. Now, if you go over the room with diffuse reflections, and that would be our case for K, for example, where you have a lot of irregular patterns that do not lead to reflections that are specular, then you find that these are invisible to the model. In this case, you only see the direct signal. The other thing that's interesting is that's also to some extent how we perceive sound. So we're able, through reflections, determine the size of the room, but if you have diffuse reflections, in that case, we don't get a big impression of the room. We can tell whether it's reverberant or not, but we don't get any of the structure. And interestingly, those do not show up in our binaural activity pattern. For this model, we also use the head movement model that works with the remapping function. And you see that one is squeezed now between the BICOM algorithm and the binaural activity pattern analysis. And basically what the remapping function does is that you take the cross-correlation pattern and it's moved with the head movement to map the cross-correlation function from ITD to a cross-correlation function to azimuth. And by moving the head virtually, we can remove the peak that's in the wrong hemisphere, front or back. I would like to refer you to our 2013 ICA paper or to our Springer article if you want to learn more about this model. But the trick is with those head movements, you can now get an unambiguous position for front-back locations. Can we use this head movement model also to predict elevation? To take it short, yes, you can. So here's an example where the sound source is located at a -120° azimuth and 30° elevation. And in the left graph, we see from back confusion, we not only see activity at -120°, but also in the opposite hemisphere in the front at -60°. It has no sense of elevation really, and that's why you see lines instead of restricted areas. However, now with the head movement, what we see is that those lines are resolved and we have a main activity at the true location -120° and 30° elevation. And that model is robust. If you want to learn more about it, it's going to be in the new Springer article that I indicate below. So what we want to do now is a binaural model simulation in the last robot lab. And we use a ray tracing model. That's the red dot is the source. We calculate the ray tracing field. The source is moving through space. We're going to stop it, and then we're going to simulate a listener through a binaural model, and that is the blue dot with the nose. So the listener is moving first, with the fronted to the nose. He's listening. He's walking through the space, and now we determine a position, and the listener is going to try to localize the sound source and use head movements to resolve front-back confusion. It's moving slightly to the left. You see two peaks in the binaural activity pattern because one is for the front direction at 0°, and the other one is at around 150° for the rear position. Now, when we move the position to the end position that moves, you see the front peak is still preserved because we handle it in a room coordinate system, but the rear peak is at a different position at -150°. If we average over all the whole movement, we'll find that the 0° preserves and the other position does not. Again, what's important in this graph is that the front is the direct signal, and then you see the reflections towards the rear. So what happens when we do it the opposite? The listener is facing to the back. Again, we see we have two peaks for the front and the back position. The two peak preserves the position. The other one shifts. So if we do an average, both average out, and now it can determine that the signal is in the back. So to conclude, we presented a model that can localize sounds in the presence of reflections. It also gets an idea about the binaural activity pattern, and it can extract, for example, information about the early reflections. So it's not only a model that can robustly localize sound in the presence of reflection, but it can also receive information about the environment itself. We then extended the model to perform head movements, which could not only help us to determine between front and back direction, but this algorithm could also be used to estimate the elevation correctly. So a few things we haven't discussed in this model. One of them is non-harmonic signals. If you read the paper that accompanies this talk, you see we talk about a substrum analysis that can be used to deal with non-harmonic signals. And then in a further chapter that will be part of our new book, Technology of Binaural Understanding, there's also simulation of a forest and a simulated forest movement. I would also like to acknowledge our sponsors, the National Science Foundation and the European Research Council. Thank you for listening to this talk. As said, Jens is in the audience to take questions. I would wish everybody a pleasant stay in Aachen, and I really regret that I can't come here because it's only about 2 hours from my hometown in Marl in Germany. Thank you very much.